Hello, and welcome to the Daily Space. I am your host, Dr. Pamela Gay, and I am here to put science in your brain. 66 million years ago, an asteroid 10 kilometers across hit the Earth, melted 10,000 cubic kilometers of rock, sent a massive tsunami crashing through the oceans, a shockwave slamming across the lands, and tossed a layer of iridium across the entire planet. This was a bad day for the planet and a really, really bad day for life that lived on land. That day was the day the dinosaurs by and large died and the Chicxulub crater formed. Unfortunately, as our world is mostly covered in water, the asteroid struck in water and formed a crater that is largely obscured by the Gulf of Mexico and visually only reveals itself through unusual structures arcing across the Yucatan Peninsula. With other forms of measurement, such as sonar from boats and seismic and gravitational data, it becomes possible to trace out not just the underwater crater, but also hidden structures inside the crater. In a new paper published in the journal Geophysical Research, a team led by G.L. Christensen collected data from sensors with direct measurements using drilled out samples. They were able to map in detail the crater's central peak, the ring that formed around the center, and the inner rim of the structure. Of particular interest to researchers studying multiple planets was the discovery that while the ring around the crater's central peak only has a few visible structures, the ring is a complete ring when the density of the crater floor is looked at. This implied that when we see incomplete rings on other worlds, they, like this crater, may simply be hiding their rings in the density profile of the ground. We'll be speaking with Dr. Christensen about this research on November 16, so please tune in then for more information. It is exceedingly frustrating that we can't go drill into other worlds. And when we try to study other planets like Mars, we have to make do with whatever we can get. Today, that means looking at rocks from Mars that were launched our way during giant impacts and studying the measurements of modern-day missions on and orbiting the red planet. Meteorites from Mars contain trapped pockets of gas from the past, while missions reveal modern atmospheric ingredients. Remarkably, we find that neon, an easy-to-lose element, has been around on Mars for a long time. Since neon doesn't stay around, its abiding presence indicates that while individual neon atoms may be escaping, the neon in Mars' atmosphere is being constantly replenished from somewhere. The most likely source is volcanic eruptions. And according to a new paper in Icarus that is led by Hiroyuki Kuroaka, this implies volcanic eruptions as recently as within the past 50,000 years. Further, since Mars still has neon to give off, it must have a lot of neon inside, and that means Mars formed fast, and that neon was mixed into Mars' internal structure before the sun began to clear out the inner solar system with its winds. Now, while this explanation is the most exciting and seems the most likely, it is also possible that dust, asteroids, and/or comets carry neon to Mars. To really understand what happened, we need a better understanding of the exact isotopes of neon on Mars. And that means we need more rocks. Those being collected by Mars Perseverance may already have the info we need locked away. Carl Sagan famously said, "To make an apple pie, you have to make a universe." It turns out that sometimes to understand the chemistry of the universe, you have to understand the pollutants of the planet Earth. Combustion processes generate complex molecules called polycyclic aromatic hydrocarbons. These large collections of atoms are part of soot and not entirely healthy to breathe. They also form naturally in massive molecular clouds in some of the colder and denser parts of outer space. According to Han Fiang Jen, during combustion, soot formation can be significant in a reaction environment that is deficient in radicals. Likewise, the temperature in the interstellar medium is too low to maintain a sufficient radical pool. And radicals produced by high energy photons in the galaxy are rare. In a new paper in the Journal of Physical Chemistry Letters, Jin leads a team that numerically models how polycyclic aromatic hydrocarbons form and the role of specific compounds, specifically butadiene. They realized that this molecule, which forms in burning organics like oil, also forms in places like Saturn's moon Titan. By understanding how the molecules form in such different environments, they're working toward changing what comes out of various industrial processes on Earth so that less harmful molecules result and we can all breathe a little bit easier. As a side note, we encountered a paper this morning documenting how the pandemic has disproportionately affected women in research. There is a now documented 20% drop in women appearing as first authors or corresponding authors on research papers. While many men have seen this pandemic as an amazing time to get ahead with less travel and fewer face to face meetings to eat their time, women have been held back by the need to take care of family as daycare for both children and elders has been shut down, and as homeschooling became the only schooling available. This disparity in expectations of men and women in the household, in the majority of households, will have long-ranging impacts on the imbalances between genders. Angel Gay Argan, study lead, points out these authorship positions are used for decision making because they reflect the degree to which researchers contributed to the production of science. The attainment of these key positions, alongside with the total number of articles published, are essential for moving up the academic ladder. Put another way, the unequal expectations placed on men and women in many homes is going to lead to women having a harder time advancing their careers and fewer women reaching senior positions. When you hear people say, women don't work hard enough to produce research, ask if those women have the same opportunities to spend their evenings doing research for fun. If they don't, maybe, take a moment to tell those women and the people critiquing them how amazing those women are for pulling off all the research they do get done, especially where works often cause them to face higher committee assignments and homes just offer them more chores to do. The world does not have equal expectations, and now it is documented. After the break, we'll be back to talk galaxies and JWST. One of the emerging themes in cosmology is finding ways to study things we really wanted to use JWST to study. Well, the potentially next great orbiting observatory has finally made its way to the region from which it will be launched. You can't count your orbiting telescopes until they have achieved first light. And as someone who planned to use the Japanese Astro E telescope for my dissertation, only to see it fail to reach its intended orbit, I have somewhat dedicated my career to seriously not counting telescopes before they launch and return healthy images. Seriously, folks, do not do it. That path only leads to heartache. And for the folks who have answered calls for observing proposals, sat on science committees, and otherwise tried to plan to use the JWST for the past decade, as it has over and over remained a couple of years or less from launch, well, finding alternative ways to do their science has become a necessity. One of JWST's science goals was to directly observe galaxies in the early universe and answer questions about how they formed and evolved in the first few billion years. These early galaxies are too faint for the largest Earth based telescopes to observe, and Hubble, while awesome, is actually a smallish telescope. Without the technology to directly observe these systems, we have to find JWST alternatives, and luckily, as we've discussed before, the universe provides. High mass systems, like massive galaxy clusters, can use their mass to bend light in the same way a lens bends light. And when a bunch of light intended for other parts of the universe gets focused our way, the too faint to see objects can become bright enough to observe. In the past on the show, we've talked about a variety of individual systems used to study specific aspects of distant galaxies. Now, a survey looks at many different gravitationally lensed galaxies to try and understand how galaxies evolved in the early universe by finding local copies. And this was a two-step process. Researchers first looked at lens systems to figure out their basic characteristics, and then they used data from the survey for high Z red and dead sources to look for nearby analogs to those distant systems. According to Alex Griffiths, lead author of a new study to MNRAS, that's monthly notices of the Royal Astronomical Society, until we have the new JWST, we cannot observe the first galaxies ever formed. They're just too faint. So we looked for similar beasts in the nearby universe and we dissected them with the most powerful telescopes we currently have. In total, they identified 27 dwarf galaxies to study and found that in general, the system showed signs of bringing star formation, binging on creating star formation, and then undergoing quiet lulls. Griffiths goes on to explain, the star-to-galaxy formation is fitful, like a jerky car engine, with periods of enhanced star formation followed by sleepy intervals. It is unlikely that galaxy mergers have played a substantial role in the triggering of these bursts of star formation, and it is more likely due to alternative causes that enhance gas accretion. We need to search for these alternatives. There is still so much science we, as a research field, require a large infrared space telescope to accomplish. We hope to see JWST launch this winter and deploy successfully. Until then, we celebrate the scientists who have found alternatives to do the research they want. After the break, we'll be back to look at other ways researchers have found interesting side routes to get the data they need. And here we are again, going to just keep going. All right. But first, I'm going to sniffle. Continuing on. When it comes to climate change, researchers have used a wide range of methods to understand the history of our planet on a global scale. We've talked before about using the movements and diets of animals, the location of mangroves, and ice cores to track just how climate has changed over the time periods around various locations. And this next story uses another method, tracking driftwood in the Arctic. A new study in the Journal of Geophysical Research Oceans, and led by Georgia Hull, retraces the journey of driftwood that has washed up on the shores of Svalbard, a Norwegian archipelago in the Arctic Circle. This journey allowed the researchers to reconstruct the level of sea ice and changes in the currents. As Hull notes, this is the first time driftwood has been used to look at large-scale changes in Arctic sea ice dynamics and circulation patterns. The press release goes on to explain, the Arctic Ocean collects trees that naturally fall into the high-latitude rivers in North America and Eurasia. When it was cold enough, some of the trees were frozen into the sea ice. The ice then floated across the ocean, swept along by the ocean currents and winds until beaching on Svalbard's shores. There they sat, some for hundreds of years, until researchers like Hull came along. The team collected driftwood and then analyzed the tree rings back in the lab. As we've mentioned before, there is a huge database of tree rings called the International Tree Ring Data Bank. And the tree rings in the driftwood were compared to samples of Arctic forests already in that database. This allowed Hole to match trees to their originating countries and watersheds and see how the sources of the driftwood varied over time. Combining that tree ring data with the earliest recorded sea ice observations from 1600 to 1850 and the more recent airplane and satellite imagery, and altogether it became possible to analyze the driftwood patterns for changes in the sea ice. The data shows that the lowest latitude sea ice, the ice in the warmest regions of the Arctic, moved steadily northward. This means the climate was warming and the ice was melting, which made it less likely for driftwood to be carried across the Arctic on the sea ice. As Hole explains, we also saw an increase in variability in the driftwood record from 1700 to 1850, which we interpret as increased variability in sea ice. When it's colder, there is more sea ice for the driftwood to travel upon, and the sources of the driftwood had a greater variability than during times when the climate warmed and the ice melted. This just goes to show that so many aspects of our planet are affected by climate change, and sea ice in particular seems to be very fragile. Speaking of tree rings, we got a little excited when we read that tree ring data was used to determine the exact year that the Vikings settled in North America. Specifically, scientists studied wooden artifacts found at the Ayance-on-Meadows, a settlement site in Newfoundland. The results of the analysis were published in Nature, and the answer to the question: the Norse settlers arrived in 1021 Common Era. Wait, why is this a planetary science story? That's the really interesting bit. Within the tree rings is evidence for an extremely rare, once in 1,000 years cosmic ray event. That event showered Earth in high energy particles back in 993 Common Era and caused a visible spike in the tree rings around the world because of the sudden increase in atmospheric carbon levels. By counting out from that spike in the rings of the fir and juniper trees cut down by the Vikings, the researchers were able to pinpoint that exact year. Understanding the process and times of Norse settlement is a lovely rabbit hole we could go down for days. And we'll link to the Smithsonian article that caught our attention in our show notes at dailyspace.org so that you can fall down that rabbit hole with us. After the break, we're going to tell you what's up in our skies and give you a brief lesson on landscape photography, because that pesky moon is almost full right now. Stay tuned. Wednesday, October 20th, was the full moon, the third phase of the lunar cycle. Various full moons get fancy sounding names like pink moon or beaver moon. These don't necessarily have a scientific reason. However, the full moon did have practical usage in keeping track of the passage of time before the industrial era. A full moon in October is called the hunter's or harvest moon and traditionally signaled the beginning of preparations for the long and cold winter in the northern hemisphere. This usually means collecting and preparing food that cannot be grown in winter for long-term storage. Full moons aren't the best time to observe with a telescope because the complete illumination washes out the fine details on the moon and the faint deep sky objects close to the moon. Objects opposite the moon will be less affected by the moon's glare. A full moon is really the time to practice your landscape astrophotography, taking pictures of ground features that happen to have something in space in the background. The full moon provides a good subject for this genre of astrophotography because it's big and bright. And also, you can make out lots of surface detail with a short focal length lens. Landscape astrophotography is also a good way to get into the hobby as a whole. The equipment it requires is minimal, like the massive telescope on a tracking mount with a special camera of deep sky or planetary astrophotography is not needed. What you need instead is just a camera and a tripod. So leave those thousands of dollars you're going to end up spending in the future for the future and go out and enjoy a low cost experience tonight. All you need is a camera with a wide or normal focal length lens, 25 to 50 millimeters, depending on your camera's sensor size. I personally love my 55 millimeter lens. You need a tripod. You can do this putting your camera on the roof of your car. I don't recommend it. You also need a remote shutter release cable. This will allow you to start and end the photo without having to actually touch your camera and make it shake. For landscapes, you might want more focal length. This will give you more detail on the object in the sky, but still allow you to have the landscape in the foreground. Like I said, I love my 55. Interesting photo compositions place the full moon on the intersection of the 2/3 lines. This means that the moon is located a third of the way down from the top, a third of the way from the left or right, just drawing your eye towards it. This uses one of the basic rules of photography, the rule of thirds, to make an interesting composition of Earth and space. You can estimate this or turn on a grid on your camera's screen to help with framing. Consult your camera's manual to see if it has this feature. Besides the moon, there are some deep sky objects that also make for interesting landscape targets, including Messier 31, the Andromeda Galaxy, Messier 45, the Pleiades star cluster, and NGC 884 and 869. These are the double cluster. M31 and M45 are well known, but you may not have heard of the double cluster. The double cluster is a pair of large open star clusters in the constellation, well, more like between the constellations of Cassiopeia and Perseus. You're missing out if you haven't seen them because it's so easy to find and it's really rewarding to observe them, especially with just a pair of binoculars. First, find the bright star Algol in the constellation Perseus. Go north until you see the W of the asterism that is Cassiopeia. Then, just south of the two middle stars and the W, that's where you can find the double cluster. Once you find it, you can frame it with a foreground object, such as a tree or a building, remembering that rule of thirds. Looking at the double cluster with a small telescope at low power with a 25 or 30 millimeter eyepiece is also a great experience, especially for a beginner just finding their way around. So go out, enjoy the wonder of the night sky. And if you do take any landscape photographs, please make sure to share them with us over on our Discord server. You can find the link at dailyspace.org. And this has been The Daily Space.